Good afternoon, everyone. Thanks for coming for our sixth seminar for the semester. Our speaker today is Dr. Yuan Zhang. He got his bachelor's and master's from Tsinghua University in China in 2006 and 2009, respectively. And then he was a PhD student with Dr. Michaela van der Schaar at UCLA. He got his PhD in 2014, and he was a postdoc with her for 6 months for a semester or so before he joined Dr. Saad as a postdoc here at Virginia Tech. He'll be talking about learning from strategic agents through repeated matching.
Yeah,
Good
okay.
luck.
Thanks for the introduction. And so this is the latest work I've done before I came here. So hopefully sometime I can present what I'm doing here sometime later. I'm sorry about date. I forgot to change the date. So it is 30 days earlier. And yeah. So this talk is about learning from strategic agents through repeated matching. And the keyword here.
Sorry to interrupt. Before you get started, just announcement. After the talk, there will be refreshments served back in the lobby there.
Yeah.
I'm sorry.
And the talk is probably much less than 1 hour, so we can go there early. So the keyword of this talk is strategic. So we are trying to learn something from some people. And because they are people, they are intelligent, and they may be strategic in the sense that they can manipulate what we can observe and what we can learn. And in this work, we are trying to develop a mechanism such that those manipulations are not profitable, such that we can learn more accurately. Okay, so I will start from a concrete example of crowdsourcing. So this is a very right now this is an emerging online application. For example, there are several online platforms such as Amazon Mechanic Turk or crowdsource microtask. So what they are doing is they provide a platform for people to post a task on the platform. And then when the tasks are posted, some workers can choose to complete those tasks. And after the completion, they will get paid by the one who proposed these tasks. And these tasks are, in general, very simple tasks and very simple and tedious tasks, like transcribe some media into text, right? Or just tag some image to see if it is if some person in the image is a man or a woman, things like this. Just very simple tasks. So the key problem in these applications is to match the correct worker to the correct task. So what do we mean by correct? It means some worker may be good at this task, some worker may be good at another task. So how to match the correct one to the given a particular task?
The worker doesn't have a choice to choose what task he wants to do.
It depends. So there are many different applications. In some applications, the worker can choose this at his freedom. In some applications, many workers will choose to try to complete one task, and the one who proposed the task can choose. And in some applications, the platform will do the matching. Yeah, I think this is a very good question. So because in this talk we are going to act as the platform, and we will match them. Yeah. So there are many works on these kind of problems. Okay, so there are some work that look at the problem from the client's perspective. So suppose I'm a client, I have some tasks and there are many workers. So how do I choose which worker to finish to do a particular task? So there are some learning framework to do this. For example, people may use multi-bandit to do this. So what they do is basically, I have a task, and based on the past history of these workers' contributions, I can learn which task is best for him. Right? So I won't go into details of this learning algorithm, but I will tell you what is missing from this. Okay. And there are some other works that look at this problem from a platform's perspective. So the platform wants to match the workers to the tasks. And how they do this? Somebody do this using matrix completion. So basically, we want to learn a big matrix. Okay, the row of the matrix is the worker, and the column of the matrix is the task. And I have observed some entry in the matrix because some workers have completed some tasks. But a lot of entry are missing. So I'm trying to learn what is, so I try to fill out this entire matrix based on the few entries that are available. And in this way, I can learn which worker does best for which task, just by completing these metrics. And there are also some works that do this by a matching framework. This is more from economic literature. So in those works, they propose some mechanisms to let the best worker to learn which worker is the best and match the best worker to the best task. But I mean, I don't want to go into too much detail about these works, but there's a common feature that is missing from all of this work. So what is missing from, well, it's not this movie. I guess I believe many of us have seen this movie. It's a really great movie. And what we learn from this movie is that even if I'm a very dumb person, right, by working very hard, I can achieve very, very great things, right? I can open a shrimp company, or I can be such a great ping pong player that I will be the ambassador of the country. Things like this. So what we learn from this movie is that the output depends on the effort a lot. So it is produced by the effort. And also, the less capable worker, by working very hard, can outwork the others. And then, if we just judge them from this output, we will match better tasks to these less capable workers. So from another perspective, it means that somebody can manipulate what we observe, right? So we don't see really the quality of the worker. We just see the quality of their output. And this can be misleading, right? So if you just match them based on this output, we may match better tasks to less capable workers. But the optimal may be, in a lot of cases, the optimal should be match the best task to the best workers and the worst task to the worst workers. Yeah. So if you don't think about this effort, we may the matching can be very suboptimal. Yeah. So well, so we don't want this to happen. So our goal is to incentivize every worker to work harder. And in the end, we can still differentiate better worker and worse workers. And we can do this by incentivizing all the workers to work harder, but better workers that have to produce a better outcome. Yeah. Okay. So we will propose some. We call this repeated endogenous matching mechanism. I will describe this.
Is this also related to matching reviewers to papers?
Yeah. So actually we will talk about it in just a few seconds. I mean, this matching, this problem of matching happens in many other places as well, not just in crowdsourcing. For example, matching authors, not authors, matching papers to reviewers is definitely a good example. So we need to learn which reviewer is good for which paper. Right? So this is also a matching problem.
Got that app coded up, let me know.
Huh?
I said, if you have that app coded up, let me know, I can use it.
Yeah, hopefully.
It's hard.
Yeah, so we will propose some mechanism such that at the equilibrium, I will define equilibrium later. Basically, this is a state where everybody wants to stay in. Okay, so in that state, better worker will always produce more, and then we can differentiate the workers' capability based on their production. So we really learn which worker is better, and which is less good. And also, we will show that in that equilibrium state, everybody is going to work harder than the case where we do not use the proposed mechanism. Okay, so this is the basic outline of what we are trying to do. And now, here comes how we do it. Right? So to do this, we first need to have a model about how these workers will act. Right? We have to build a model for these agents. Right? So in particular, we say in the system there are workers and tasks. Right? The workers have a tag W. It is uniformly distributed in 0 and 1. So if I'm worker 1, it means I'm a very good worker. If I'm worker 0, I'm the worst. Okay. And there's some, we can define some productivity function that depends on my type. So the simplest one is that the productivity is just the same as my type. Or it can be the square of my type, or square root of my type. You can define many productivity functions as long as it satisfies some basic properties of being positive, increasing in type, concave, and twice differentiable. So these are our technical conditions. But there are many productivity functions that satisfies our assumption, right? And then each worker get to choose an effort level, right? The key feature we talked about earlier, which was not modeled in those previous works. Okay, so this effort is what I can choose, and based on the effort and my type, there's a cost. So if I'm the best worker and I choose effort 10, I have a cost. But by choosing the same effort, suppose I'm worker 0 and I choose the same effort, then my cost may be much higher. So there's also some properties of this cost that needs to be satisfied. But those are very natural assumptions. So the cost is increasing in the effort and decreasing in the worker type. So if I'm a better worker, my cost of exerting effort is smaller, right? And we also model tasks. The task is also uniformly distributed in 0 and 1. And the task 1 is the best task. The task has the most importance. The task 0 is the worst task, the least valuable task. Okay, and we can define a function, the quality function, that depends on the task type. Right.
So the quality be associated with the user as well.
So here, this quality only models how important the task is so actually the output when a worker completes a task, the output will depend on everything, on both workers type and so this y function, this is the output. It depends on the worker's type, how good I am. It depends on how important the task is, and depends on my effort, right? So this is the output function, and we want to maximize the total output. Okay, and there is also a payment. That is, the platform will give some commission to the workers if they finish the task. And how much they get depends on the output, the final output. So the workers' payoff will be this payment minus cost. So this is my payoff, and I want to maximize this payoff as a worker. So this is the workers model. So and there's our favorite example that is we will use this a lot next to illustrate some concepts. So the cost, so the output is just the product of effort and worker type and task. Right? The payment is linear in the output, and the cost is quadratic in my effort, and the worker's payoff is then can be written here. So this is just a very simple example, but it's also reasonable, and that satisfied all the assumptions of our model. Right. So in this scenario, the designers, that is the platform the platform designer who provide this crowdsourcing market, right? So this designer knows the task, so which task is more important and which task is less important. So I will know this, and I also know the worker's output history. So I can observe that when this worker finished this task, how good he finished it, right? How good his production is. So I will know this, but I only know this. I don't know anything else, like how good is this worker. So I don't know the worker's type. I can only know his output. And I also don't know is cost function or output function, all these things. And I can definitely not observe this effort. And as a worker, if I'm a worker, I only know my own type for sure. And I will know my own output history. And I will know output distribution. That is, at current time slot, what is the output distribution of the entire population? Like, for example, if there are 10 workers, for example, how many workers have an output of 10, and how many have an output of 9, how many have an output of 0? So I will know this. This is kind of like a probability distribution of the output. But I don't know specifically what is the production of this worker and what's the production of that worker. Okay. So and this statistic of the output distribution will be displayed by the platform. So this is actually part of our mechanism. We propose that the platform should display this information, this output distribution. And this will not violate the privacy of the other workers. This is just statistics, right? And this will be useful to incentivize the workers to work harder. And then the worker does not know, apart from this, it doesn't know anything else. Okay, so let's do some, just think about some simple cases on this canonical example. Okay, so we want to consider first a case, an upper bound that is not achievable. So in this case, we assume that the form or the platform, it has complete information. So it knows exactly the type of each worker, right? And somehow it can tell the workers to do anything, basically. So in this case, first the optimal, because we already know the workers' types, so we can do the optimal matching. That is, match worker W to task W. That is to match the best worker to the best task and the worst worker to the worst one, right? So the matching is this. And then we incentivize the workers to exert the highest effort. That is so each so the pointer is not. Okay, so we let each worker W to choose the effort E such that my final payoff is 0. So this is my W is my type, and my task is also W. So given the effort E, my output is W squared times E, right? And the payment is lambda times my output. So this is what I get paid. And this E squared is my effort. So somehow they just impose me to exert this very high effort. Okay. And they cannot let me to work harder, because if I choose an even higher effort, my payoff is negative. Then I can choose not to do anything at all. I can choose not to participate, right? So this is basically the highest effort I can choose, subject to the fact that to the constraint that I get a non-negative payoff. Okay, and then we can compute the effort level. This is the highest effort level I can choose. And then based on this, we can compute the worker's output, and then the firm's profit. So basically the profit is we have a total output, and we give a fraction of lambda to the workers, and the rest is my profit. And we do some calculation and find that the final output, the total output, the total output of all the workers. So we do an integration over the worker type. That is 1/10. So in this simple example, and this is the first best output level. It means if the worker, if this platform has complete information, we can let the worker do anything. This is what we can achieve. And in the real world, this is not achievable because you cannot just let me do anything, right? And we have another benchmark, that is the form has complete information still, so it still knows the workers types. So the learning is done here, but I don't have a good matching mechanism. Okay, so in this case, what we can achieve is as follows. So because we know the workers type, we can still do the optimal matching, right? And then I cannot let the workers do anything. The workers has to maximize. Which is very natural. The worker will maximize its payoff. So it will choose an effort level that maximizes this payout function. We can compute this optimal effort level as this. This is actually 1/2 of the previous effort level. And hence, in the end, we can compute the final total output. It is only 1/2 of the first best. So basically, suppose there's no learning to do, and I have complete information about workers type. If I can do anything, I can achieve the first best. But if I have to respect the workers' incentives, we can only achieve 1/2 of the first best. So we will propose a mechanism that in this mechanism, I do not know the workers' types. Okay, so I don't have complete information. But by doing some clever matching mechanism, I can achieve a higher output than this one. Right. Okay, so what is our matching rule? Our matching rule is as follows. So we have incomplete information, right? That means we don't know the workers' type, so we cannot do the matching just based on their types. But we do observe their production, so we will match them based on the production. So in particular, in the system, time is slotted, right? And at each time slot, we just rank each worker in terms of their production. So if I have a higher production than half of the workers, I will be matched to task 0.5. That is a task that is better than 50%, 1/2 of the tasks. So this is our matching mechanism. It is quite a simple matching mechanism. We just run them by the production, by the output, right? And then the future task is matched based on this ranking. Okay. But this is different from the previous matching rule that doesn't work very well, because if you think about this, my current effort affects my current output, right? And my current output affects what task I match to in the future. So in this case, I have an incentive to maximize not only the current payoff, but also the future payoff. So I won't be myopic. I will think about the future. So I may be incentivized to work harder in order to get a better task in the future, right? So this is a basic idea, and we show that it really works. We will incentivize workers to have a higher output, right? Um, and and but there is a potential problem with this matching rule. That is, since the worker is not myopic anymore, I'm not just maximizing the current output. I also think about the future. So when I choose my effort, the problem I'm trying to solve becomes much more complicated. Because I need to think about the current payoff, which is simple. You saw the equation of my current payoff, right? We know the form of the current payoff. But in the future, my future payoff is very hard to compute for several reasons. The first reason is I cannot predict what the other workers do, right? And my future payoff depends on what task I match to. And what task I match to depends on what the others do. Because they're going to rank me. They don't match me based on my absolute production. It matches me based on my relative ranking of the production. And that depends on the others a lot, right? So it's very hard for me to predict what the others are doing in the future, in the long term. So
Is it possible to achieve optimum in finite time?
In finite, so you mean by that, do you mean I'm maximizing in a finite time horizon, or
But because you're looking at future rewards as well, I mean, I guess probably if I see that.
yeah? So in this case, we assume that these workers will maximize the entire sum payoff over an infinite time horizon. Yeah. Yeah. So for the finite horizon case, it will become much more complicated. Yeah.
Probably the discount factor can take care of the time horizon, maybe then.
So the discount factor will.
Maybe the platform gives you, tells you a priori that the tasks have to be finished by so much amount of time. And maybe everyone, all the workers know.
That time, the deadline of completing a task, that is modeled like a one time slot. So time slot is about that time, but the time horizon, infinite time horizon, means I may envision that me doing a lot of tasks in the future, and there is some uncertainty of when I will stop. So this is one justification for the infinite time horizon model. We can think about this discount factor as the probability that I stop. So yeah. Yeah, so this is what I just said. It's hard to solve this problem exactly. Solve the workers' optimization exactly. So we will propose some simpler model for the workers. So in this model, the workers will have a bounded rationality. So what do I mean by that is I will not attempt to predict what the output distribution will involve in the future. I will just assume that the output distribution is the distribution will stay the same forever. So I see the current output distribution, and I assume it's fixed. It's fixed in the future. Right? So this makes easier for the workers to solve its own optimization problem. Yeah. Okay, so I won't go into detail how it solved, but still I have to define an equilibrium. Right? So the equilibrium is a state where everybody wants to stay in. So this is an important state of the system. So so we will study assortative equilibrium because so what we mean is that in this equilibrium, we have to specify two things. One thing is the output distribution, the statistics of other workers' output, right? And another thing we need to specify is the worker's strategy. That is, what effort level I should choose at each time slot. Okay, and these two combined can constitute an equilibrium if two assumptions are satisfied. The first assumption says, so under this particular output distribution, the strategy is the optimal one, the one that maximizes my total output. So in other words, I'm really incentivized, so I'm not forced to do anything, right? Another requirement is consistency. That is, if I choose this strategy, and if everybody else chooses this strategy, the resulting output distribution is really this output distribution in the equilibrium. So this incentive compatibility and consistency needs to be satisfied in the equilibrium. And
Is this the same distribution you assume now? You assume that the distribution is fixed.
so what happened is at the beginning the platform will tell me what is the distribution. And when I optimize, I assume this is fixed. But in the next time slot, it may change, right? Because we may choose before the convergence to the equilibrium. In time slot 2, it may change again. So I learned that new distribution, and I again assume this is fixed and do my optimization. And in time slot 3, it may change again. But under some time, in the end, they will converge to the equilibrium, where the distribution will not change anymore. So this is a state where the system finally settled.
Does it happen because I don't know anything about the other user? Does it work mainly because the platform is telling you the distribution?
Yeah, exactly. So basically, if I know the distribution, I don't know anything else about the other users, because the others only affect me through my ranking in the output distribution.
So I'm asking this because in the 802.11, there's a multi-user MDP when different MDPs are coupled with each other. And when you cannot separate those MDPs, there's no way you can come to an equilibrium. Because I do not know anything about your MDP, you don't know anything about my MDP.
Yeah.
So there's no way to come to an equilibrium in that case. Unless the centralized server tells me that this is the distribution of the in that problem specifically, it tells me the distribution of the contention windows, for example.
Yeah. So
if someone tells me something, then probably I can sort of decouple the MDPs, but maybe not. If the platform doesn't tell me, then probably this may not converge at all, right?
Right.
They just ping ponging going on all the time.
Right. So I guess in general, if there are a lot of people, agents in the system, I have to know something about the others. If I don't know anything at all, we don't know where the system will go. Yeah. And so this turned out to be a midfield game. So if you haven't heard about it, it is a relatively new game theoretical concept. So it's called midfield games. And there are a lot of results in midfield games to prove the existence and uniqueness of the equilibrium. But what we are trying to say is the existing result in midfield games cannot be applied here for several reasons. For example, one reason is my effort level is a continuous variable, and it can take value from 0 to infinity. So in this action set, if the action set is like this, the result cannot be directly used. So what we want to do is to not only prove, so we need to develop some new tools to prove the existence and uniqueness of the equilibrium. So let me briefly describe the result first. So the first result is that this equilibrium really exists. So we are not talking about a system where the equilibrium does not exist at all. So this model is really a meaningful model. And the equilibrium exists, that means we can learn the workers' types. Right? So we solve the learning problem. And also another important property of the equilibrium is the uniqueness. And it's always, if you know a little about game theory, uniqueness is not always there. So the equilibrium in general is equilibrium. Is unique only under some conditions. And in this particular case, the sufficient condition for uniqueness is that it's either one of these two. So suppose I'm the worst worker and I match to the worst task. But still our output may be positive. We can still produce something. So if that's the case, then the equilibrium is unique. Okay, so I guess this is a fairly general condition because in a lot of cases, even the worst worker and the worst task, they can produce something. Their production is not strictly zero. Yeah. And if the cause is of particular form, the equilibrium is also unique. And finally, we also prove that under this mechanism, the equilibrium output level is really higher than the one that we do not adopt this mechanism. So every worker will work harder in this incentive scheme. So I guess I will skip how we prove these results. Again, I want to emphasize that if you are interested, this is a new tool to prove the existence and uniqueness of equilibrium in this type of midfield game. When the existing results do not apply, okay, and yeah, okay, so we go back to the canonical example and see what is the total output under our incentive scheme. Okay. So after some calculations, again I won't go to detail of how we compute this, but somehow in this canonical example we can compute the equilibrium output distribution as this. So here lambda is the fraction of payment, right? And delta is the discount factor. It is how we discount the future. And this delta is from 0 to 1. So if delta is 0, it means I only care about the current fail. If delta is 1, it means I treat the current fail and the future fail equally. if delta is between 0 and 1, it means I will discount the future payout a little bit. It's like the something like the interest rate. It's like I will discount the future money I get when I compute the current money I have. And this W is the worker type. So for the worker 0, I will produce 0. For the worker 1, I will produce 1. So this is the equivalent output level. And just based on this equivalent output level, we can compute the final output. So this is the final output. And we want to compare it with the two benchmark we introduced earlier, right? If you remember the first best, that is, as a form, I know everything about the workers. There's no learning to be done, and I can enforce them to do anything. Okay. In this case, the total output is 1/10. And in the other benchmark, I still know everything about workers, and there's no learning to be done. But I cannot enforce them to do anything. I need to respect their incentives. Right? In that case, I achieve 1/2 of the first best. So what we can achieve is between these two, and in particular, if the discount factor is 0, that means if the worker is completely myopic, I don't care about the future at all, then our mechanism will do the same as the naive mechanism, because our matching relies on the fact that my current effort and my current output affects the future task I match to, right? But if a worker is completely myopic, doesn't care about the future, then our mechanism will not work. And in that case, we achieve exactly the same as that myopic benchmark, which makes sense, right? But if the workers are not myopic, they care about the future. I mean, people usually care about the future, right? And then, in the best case, if they care about the future a lot, this delta is 1, we can achieve about 2/3 of the first best. And that is about 30% better than the myopic benchmark. Yeah, so in conclusion, we propose some mechanism that can incentivize, that can help a designer to learn better in an environment where the workers can strategically choose this action and hence influence what I can observe and what I can learn. So under this mechanism, we can really learn the true types of the workers and then also incentivize them to work harder. Yeah, so this is I guess that's it for the talk.
What happens if there is a malicious user? If
Uh,
someone
mo-
is trying to manipulate distribution.
Yeah, so suppose malicious in the sense that I don't even care about my own payoff. Yeah, so in this work, we are assuming each worker are rational and we are maximizing my payoff. So if there's so suppose I just want to exert a very high effort level and such that people cannot get the best task, right? Even though that means I exert a very high effort level, incurs very high cost, and I don't get much, and I may get even a negative payoff, right? So, so in this, so actually it depends on how many workers there are. So for example, in the current model, we assume a continuum model. So that is, there are infinite number of workers. Their type is from 0 to 1. So if there's just one worker do this, it doesn't matter, because suppose I'm better than one half the worker, one half of the worker, and one infinitesimal worker from the bottom half is malicious and do some irrational things. Basically, from the merit theory point of view, I'm still ranked better than one half the worker. Of course, if there are just a few workers, there will be problems. Yeah, so
Would
I
your
guess
definition of equilibrium change in that case?
We can still define the equilibrium in the same way for those rational agents, and we assume those malicious agents are exogenous. And then there could be still some equilibrium notion, right? But I guess from a platform designer's point of view, I may not. So on one hand, I may not care too much about those type of malicious users, because I don't care about their cost. I only care about the output. So if they want to,
It will impact the other workers, right?
yeah. So the effect I'm worried about is that those type of malicious user may discourage the rational users. So that is an interesting question, actually. Actually, you haven't thought about that, but it's definitely an interesting problem to think about. Yeah.
I have two questions. The first one is, in your model, do you assume all users have the same behavior history? Or in other words, do you allow those workers to leave and join the system?
So I guess these are two different questions. So first, we don't allow them to leave and join the system repeatedly. So we assume that they just stay in the system for a given long time horizon. But even in this case, they can have different behavior history. I mean, they can behave completely differently. Their effort levels in the past can be
How
completely.
about the length of the history? Do you allow them to start at different times? The reason I'm asking this is because I'm thinking whether this may relate to how long you have been staying in the system, or how long is your
Well, so
Everything is assumed to be infinite here, right? Anyways, the platform is giving you the distribution.
I'm thinking if two workers that have the same capacity and that they join the system at different times, and after a while will they end up being with the same output?
so I guess because we have a infinite horizon model, the time where you arrive doesn't matter a lot. In the final state, it seems those finite small difference in the times where you join the system, it does not matter a lot.
For the newly joined worker, there's no
Um,
history or no record
yeah,
of what type of work.
because the mechanism does not depend on your complete past history. So when I match a person, I only look at the previous output. So I only look at output at the previous time slot, not anything earlier. So So in this sense, the length of the existing history doesn't matter. So if I stay here for 10 days, you only stay here for 1 day, still I match you based on our output in the previous 1 day. So my past 10 days, 9 days doesn't matter.
I have another question. Just curious, if from the platform's perspective, like giving a false distribution, like always telling the workers you're not good enough,
Yeah.
intentionally telling you a lower ranking or a real ranking, well, that doesn't motivate the workers to work harder.
I guess there are actually two conflicting effects. I mean, if I want to do this, I have to do this in a very careful way. So I don't want to. I guess if I have a slightly higher false output distribution, I can incentivize them more to work harder. But if I do this too much, I may discourage them because they will see based on such a high output distribution, in order to be ranked high in this output distribution, I have to exert such a high effort that maybe my payoff will be zero and will be negative. So in that case, it's not good for it won't incentivize me. So 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 how to choose this false output distribution is a tricky problem actually. Yeah. So especially because I don't know anything about the users. I don't know their cost function, output function. So it's very hard for me to choose such a output distribution. So I may be better off just give them the correct information.
So in a related kind of question, so now you're assuming in the model that the current distribution is going to remain for the future time step. So when I take a decision now, I assume that how I rank, if I do the same after, it's going to be the same for the next time step. Okay.
Yeah.
So what if the subjective perception of the participant is that everyone is going to work harder than they are working now? So they're going to be scared that everyone's going to outperform them and they're going to go down in the ranking process. So that will give them a push to perform more, but at the same time they can reach a point where their payoff might be negative. So if you do that adjustment, do you think that the final output
Yeah.
be
So
better from the system?
yeah, this is a good point. So basically, we view the model for the agent that has bounded rationality. That is, I don't know anything. So I have to, because I don't know anything, I have to assume something for what the others are doing, right? And what models I have, there can be many different models. I can be how do I say? I can be a very anxious person. That I'm always afraid that the others are going to work harder and harder and outperform me. Or I can be some person that is very laid back. I think the others are just maybe they are tired and they won't exert the same high effort in the future. Yeah, so there are many possible models for the agent, and they all make sense, I think. So in this work, we choose one. We choose one of them. But how? I mean, intuitively, if I'm an anxious person, I should work harder and harder, and everybody work harder and harder, and the equilibrium output is higher. But
In the equilibrium should tend to that point where the 1/10 becomes the most important first. Right.
I'm not sure I don't think 1/10 is achievable because in that case everybody have zero payout.
I mean,
I don't.
asymptotically.
Yeah, asymptotically, maybe we can approach that, but we can never really achieve 1/10 because I don't think in any equilibrium I can have zero payoff because in that case I can always work less hard and have some positive payoff. So that cannot be equilibrium, but we may approach 1/10, or maybe there is a bound. Yeah, that is an interesting question.
Any more questions? Okay, that's
Okay,
nice.
thank you all.